Guidance for inspectors on-stream and off-stream inspection of above-ground storage tanks based on API 653 and EEMUA 159, best practices for inspecting storage tanks safely and effectively. Please note that this presentation reflects the presenter's perspective only. Introduction to above-ground storage tank inspection, scope and objectives of on-stream and off-stream inspection, applicable standards, API 653 and EEMUA 159. Above-ground storage tanks, ASTs, are critical assets in the oil, gas, petrochemical, and terminal industries, used for the storage of crude oil, refined products, chemicals, and intermediates. Due to their large size, long service life, and exposure to environmental and operational stresses, ASTs are subject to various degradation mechanisms such as corrosion, settlement, fatigue, and mechanical damage. Effective inspection is therefore essential to ensure continued safe operation, environmental protection, and regulatory compliance. This presentation provides structured guidance for inspectors performing both on-stream, in-service, and off-stream, out-of-service, inspections of ASTs. Aligned with the requirements and recommendations of API 653 and EEMUA 159. API 653 is widely adopted for tank inspection, repair, alteration, and reconstruction, while EEMUA 159 provides a complementary integrity management and risk-based approach. Together, these standards establish a comprehensive framework for assessing tank condition, determining inspection intervals, evaluating fitness for service, and planning maintenance or repair. Inspectors must understand not only what to inspect, but also why each inspection activity is important, how findings relate to acceptance criteria, and how results influence future inspection planning. This introductory slide sets the context for the remainder of the presentation by emphasizing the role of inspection in asset integrity management, the responsibilities of inspectors, and the importance of applying both prescriptive and risk-based principles. A consistent, standard-based inspection approach supports safe operation, reduces the likelihood of leaks or catastrophic failures, and helps organizations manage aging tank populations in a cost-effective and defensible manner. The scope of AST inspection under API 653 and EEMUA 159 includes both on-stream and off-stream activities, each serving distinct but complementary objectives. On-stream inspection refers to examinations performed while the tank remains in service, typically focusing on external components, accessible areas, and condition monitoring techniques that do not require product removal. The primary objective of on-stream inspection is early detection of deterioration, confirmation of continued fitness for service, and identification of conditions that may necessitate corrective action or an out-of-service inspection. Off-stream inspection, by contrast, is conducted when the tank is taken out of service, cleaned, and made safe for internal access. Its objective is to allow detailed examination of the tank bottom, internal shell surfaces, welds, and other critical areas that cannot be adequately assessed during operation. Together, these inspection types support a life cycle approach to tank integrity. API 653 defines minimum inspection intervals, examination methods, and acceptance criteria, while EEMUA 159 emphasizes inspection planning based on risk, degradation mechanisms, and consequence of failure. Inspectors should understand that inspection is not an isolated activity but part of an integrity management loop that includes data collection, assessment, decision-making, and follow-up actions. Clear definition of inspection scope and objectives ensures that inspection resources are focused on the most critical areas, that inspection results are meaningful, and that safety and environmental risks are effectively managed. API 653 and EEMUA 159 are the primary standards governing the inspection and integrity management of above-ground storage tanks. API 653 provides detailed, prescriptive requirements for inspection intervals, examination techniques, minimum thickness calculations, acceptance criteria, and repair methods. It is particularly strong in defining what must be done to demonstrate compliance and continued fitness for service. EEMUA 159, on the other hand, focuses on integrity management principles, encouraging a holistic and risk-based approach that considers degradation mechanisms, operational history, inspection effectiveness, and consequence of failure. while API 653 is often used as the regulatory or contractual baseline. EEMUA 159 supports more optimized inspection strategies through risk-based inspection, RBI, and long-term maintenance planning. Inspectors should be familiar with both documents and understand how they complement each other. In practice, API 653 requirements are typically treated as minimum standards, while EEMUA 159 provides guidance on enhancing inspection planning, prioritizing resources, and justifying interval extensions or alternative inspection techniques. Knowledge of both standards enables inspectors to make sound technical judgments, communicate effectively with engineers and asset owners, and ensure that inspection findings are evaluated within an appropriate integrity management context. Purpose and limitations of on-stream inspection: external visual inspection of tank components, shell thickness measurement and corrosion monitoring, roof, settlement, and ancillary system checks. On-stream inspection plays a crucial role in monitoring the condition of above-ground storage tanks while they remain in service. The primary purpose is to identify visible deterioration, monitor corrosion rates, and confirm that the tank continues to operate safely within its design and assessment limits. On-stream inspections help detect issues such as external corrosion, coating breakdown, leaks at nozzles, roof damage, settlement, and malfunctioning ancillary systems. These inspections also provide data to validate corrosion assumptions, update inspection intervals, and determine whether an off-stream inspection should be advanced. However, inspectors must clearly understand the limitations of on-stream inspection. Internal components such as the tank bottom, annular plates, and internal shell surfaces cannot be directly examined while the tank is in service. Indirect techniques, such as ultrasonic testing, UT, of the shell or settlement monitoring, provide valuable information but do not replace the need for internal inspection. API 653 specifies minimum external inspection intervals, while EEMUA 159 emphasizes understanding inspection effectiveness and uncertainty. Inspectors should therefore treat on-stream inspection as part of a broader inspection strategy, recognizing both its strengths and its inherent constraints. Clear documentation of findings and limitations is essential to support informed integrity decisions. External visual inspection is the foundation of on-stream tank assessment and should be conducted systematically and thoroughly. Inspectors should examine the shell for signs of corrosion, coating degradation, bulging, denting, cracks, or product staining that may indicate leakage. Roof systems, whether fixed or floating, should be inspected for structural damage, corrosion, missing components, or abnormal deformation. Particular attention should be given to roof seals, pontoons, drains, and support structures. Nozzles, manways, and flanges should be checked for leaks, gasket deterioration, and corrosion at the shell-to-nozzle interface. The tank foundation and surrounding area should be assessed for evidence of settlement, erosion, cracking, or inadequate drainage. API 653 requires regular external visual inspections, typically at intervals not exceeding 5 years, while EEMUA 159 encourages more frequent walkdowns based on risk and operating conditions. Inspectors should use checklists to ensure consistency and completeness, take photographs to document conditions, and record observations in sufficient detail to support trend analysis. External visual inspection often provides the first indication of developing integrity issues and is therefore critical to effective tank management. Shell thickness measurement using ultrasonic testing is a key element of on-stream inspection under API 653. The objective is to determine remaining wall thickness, calculate corrosion rates, and verify compliance with minimum required thickness values. Measurements should be taken at representative locations on each shell course, with increased coverage in areas where corrosion is suspected or where historical data indicates higher corrosion rates. API 653 provides guidance on the minimum number of measurements and the evaluation of results, including the calculation of remaining life and inspection intervals. Inspectors should ensure that UT equipment is properly calibrated, surface preparation is adequate, and measurement locations are accurately recorded for repeatability. EEMUA 159 emphasizes the importance of corrosion monitoring within an integrity management framework, including understanding corrosion mechanisms, variability, and uncertainty. UT data should be trended over time to identify changes in corrosion behavior and to support risk-based decision-making. Accurate shell thickness data is essential for ensuring structural integrity, preventing leaks, and justifying continued operation. In addition to shell inspection, on-stream inspection must address roofs, foundations, and ancillary systems that contribute to overall tank integrity. Floating roofs should be inspected for pontoon integrity, deck corrosion, seal condition, and proper drainage, as failures can lead to product loss and emissions. Fixed roofs require examination of plates, rafters, columns, and vents to ensure structural soundness and adequate pressure relief. Settlement monitoring is critical, as uneven settlement can introduce high stresses in the shell and bottom. Inspectors should review settlement survey data, visually assess foundation condition, and look for signs of distortion. Ancillary systems such as cathodic protection, fire protection, and overfill prevention devices should also be checked for operability and condition. API 653 references these elements, while EEMUA 159 places them within a broader risk and consequence context. Comprehensive on-stream inspection ensures that all elements influencing tank safety are considered, not just the primary pressure boundary. Purpose and preparation for off-stream inspection, internal visual inspection of bottom and shell, tank bottom inspection using MFL and UT, evaluation, acceptance criteria, and hydrotesting. Off-stream inspection provides the most detailed and reliable assessment of above-ground storage tank condition and is a cornerstone of API 653 compliance. The primary purpose is to enable full internal examination of the tank bottom, internal shell surfaces, welds, and critical zones that cannot be adequately assessed while the tank is in service. Proper preparation is essential to ensure both safety and inspection effectiveness. This includes removing product, cleaning the tank, gas freeing, and confirming that the atmosphere is safe for entry. Confined space entry procedures, permits, and safety briefings must be strictly followed. Inspectors should review historical inspection data, repair records, corrosion rates, and risk assessments prior to entry to focus inspection efforts on the most critical areas. EEMUA 159 emphasizes planning inspections based on expected degradation mechanisms and risk, rather than a purely checklist-driven approach. Effective preparation ensures that off-stream inspection activities are efficient, thorough, and aligned with integrity management objectives. Internal visual inspection is the first step once safe entry into the tank has been established. Inspectors should systematically examine the tank bottom for general corrosion, pitting, grooving, and localized thinning, paying particular attention to the annular ring and critical zone near the shell-to-bottom weld. Evidence of underside corrosion, product contamination, or water accumulation should be noted. Internal shell surfaces should be inspected for corrosion, coating breakdown, weld defects, and mechanical damage. Weld seams, including vertical and horizontal joints, should be closely examined for cracking or corrosion-related defects. Visual inspection findings guide the selection and extent of non-destructive examination such as MFL or UT scanning. API 653 requires thorough internal visual inspection, while EEMUA 159 stresses understanding degradation patterns and their implications for future integrity. Accurate and detailed recording of visual observations is essential for subsequent assessment and repair planning. Tank bottom inspection is one of the most critical components of off-stream inspection due to the high risk associated with bottom leaks. Magnetic flux leakage, MFL, scanning is commonly used to provide full coverage of the tank floor, identifying areas of metal loss, pitting, and corrosion. MFL results should be reviewed by qualified personnel and followed up with targeted ultrasonic testing to quantify remaining thickness. UT measurements confirm the severity of indications and support fitness for service assessment. Inspectors must ensure proper calibration, coverage, and data recording for both techniques. API 653 specifies acceptance criteria for bottom thickness and guidance on repair or replacement, while EEMUA 159 emphasizes interpreting inspection data within a risk-based framework. Effective bottom inspection enables informed decisions on repair scope, remaining life, and inspection intervals, directly supporting environmental protection and operational safety. Following off-stream inspection, inspection data must be evaluated against acceptance criteria defined in API 653 and guided by EEMUA 159 principles. This includes comparing measured thicknesses to minimum required values, assessing corrosion rates, and evaluating weld defects. Critical zones, such as the annular ring and shell-to-bottom weld, require particular attention. Where repairs or major alterations are performed, hydrostatic testing may be required to demonstrate structural integrity and leak tightness. Inspectors play a key role in verifying that repairs meet standard requirements and that hydrotest procedures are properly executed and monitored, including settlement observations during filling. EEMUA 159 encourages considering long-term integrity and risk implications, not just immediate compliance. Clear evaluation and documentation ensure that inspection results translate into effective integrity management actions. Common degradation mechanisms in ASTs, non-destructive examination methods, documentation, reporting, and RBI integration, inspector competency and safety requirements. Understanding common degradation mechanisms is essential for effective inspection planning and execution. ASTs are susceptible to uniform corrosion, localized pitting, microbiologically influenced corrosion, (MIC), erosion at nozzles, and underside corrosion of tank bottoms. Environmental factors, such as humidity, temperature, and soil conditions, as well as operational factors like product type and water content, influence degradation rates. API 653 requires inspectors to consider corrosion mechanisms when selecting inspection locations and methods, while EEMUA 159 emphasizes identifying credible damage mechanisms as part of risk assessment. Awareness of degradation mechanisms enables inspectors to focus on high-risk areas, interpret inspection findings correctly, and communicate potential integrity concerns to engineers and asset owners. A range of non-destructive examination (NDE) methods is used in AST inspection to detect and quantify defects without damaging the asset. Common methods include ultrasonic testing for thickness measurement, magnetic flux leakage for tank bottoms, magnetic particle testing for surface breaking defects in ferromagnetic materials, and penetrant testing for detecting surface cracks. Advanced methods such as phased array UT may be used in critical areas. Inspectors must understand the capabilities and limitations of each method, ensure they are applied by qualified personnel, and verify that results are properly interpreted. API 653 references acceptable NDE techniques, while EEMUA 159 highlights inspection effectiveness and reliability as key considerations in integrity management. Comprehensive documentation is a fundamental requirement of both API 653 and EEMUA 159. Inspection reports should clearly describe inspection scope, methods, findings, measurements, and conclusions, supported by photographs and NDE data. Accurate records enable trend analysis, support regulatory compliance, and provide the basis for repair and maintenance planning. Inspection results should be integrated into risk-based inspection (RBI) programs, where applicable, to update risk rankings and adjust future inspection intervals. EEMUA 159 strongly advocates the use of RBI to optimize inspection effort and focus on high-risk tanks or components. Inspectors play a critical role in ensuring that inspection data is reliable, complete, and suitable for risk assessment and integrity decision-making. Inspector competency and safety awareness are essential for effective AST inspection. API 653 requires inspectors to be properly qualified and certified, with demonstrated knowledge of tank construction, inspection methods, and acceptance criteria. Experience and ongoing training are critical to maintaining competency. Safety considerations are particularly important during off-stream inspections involving confined space entry, hot work, and the use of NDE equipment. Inspectors must comply with site safety procedures, permit-to-work systems, and hazard controls. EEMUA 159 reinforces the importance of competent personnel and strong safety culture as part of asset integrity management. A competent and safety-conscious inspector contributes directly to reliable inspection outcomes and safe tank operation. Summary of best practices for AST inspection. Effective inspection of above-ground storage tanks requires a structured approach that integrates on-stream and off-stream activities in accordance with API 653 and EEMUA 159. On-stream inspection provides ongoing assurance of external condition and operational integrity, while off-stream inspection enables detailed internal assessment of critical components. Inspectors must understand applicable standards, degradation mechanisms, inspection methods, and acceptance criteria, and must document and communicate findings clearly. Integrating inspection results into integrity management, and RBI processes supports informed decision-making and optimized inspection planning. By applying best practices and maintaining high standards of competency and safety, inspectors play a vital role in ensuring the safe, reliable, and environmentally responsible operation of ASTs throughout their service life.